Okay, so let's give a quick introduction about medical research paper. So I don't know how much I've dealt with scientific papers in general. There are many kinds of papers that you can find in scientific journals. Probably the most common by numbers is research articles. These are the ones that you really expect as a research paper. So somebody did an experiment and they report what they found and they describe how they did it. That's it. There are the meta-reviews. These are statistical compilation of findings. Let's say in the medical, and especially in the medical field, these are the most relevant because there is a very typical bias when you do a research paper and you generally find that your experiment worked, whatever your experiment was. In the meta-review, you collect all the papers that did experiment about a certain topic, like whether some drug works for some disease. You compile the statistical results all together from all the experiments, and you need to be super careful about selection bias. So you want to take every single paper that has ever been published about that topic, and you compile the results, and you see if they all agree with one another in the statistical meaning agreement. Then there are editorial reviews, so some experts discuss about their opinion about one topic, and then other kinds of papers like comments, opinions, dissemination, education, and other things. Now, physicians or life scientists in general write papers with 4 specific chapters or sections. That's absolutely not the case like for programmers or mathematical scientists. If you take a paper, an AI paper about something, you will get a free-form paper. They have 5, 6, 7, 8 chapters, and generally the first one is introduction, and at the end of the introduction there is a paragraph saying this paper is structured as follows. Like they did for experiments, and they do one chapter for each experiment, or they do theory and experiments, and they have one chapter for each. While life scientists inevitably use this structure: introduction, materials and methods, results, and discussion. In the introduction, they provide the background about the issue. They might overdo that, but in general, the important part is the previous research of this topic. You need to know where you're starting from, the details about the pathology they're researching, the importance of what they're doing, and especially they should introduce the way that they decided to apply to their specific problem. Now, materials and methods, that's really, especially for us, the single most important chapter, because here they provide all the information needed to replicate the study. So you should be able to read this chapter and be able to do the same and get the same results within the statistical variance. So if they worked with patients, they need to report strictly how they were chosen, including inclusion and exclusion criteria, which is where the bias comes in. They should report about compliance with ethical standards. And the procedures they performed, which for us means which image acquisition were performed, how images were processed for the acquisition and pre-processed, like you do a CT scan, and I don't know, like you want to detect lung tumors in a CT, it makes a difference whether you use the state-of-the-art CT scanners using the high-resolution protocol with high dose, or whether you are using old scanners and doing the 5 millimeter slices with the lowest possible dose on everything else that happened afterwards. And This is very important because people generally talk about qualitative terms. This is good, this is bad, but when you define the outcomes, you really want to go to say how the outcomes, like there was a tumor, and how do you know? Did you get the biopsy afterwards? Did you do 3 years follow-up? And so on. And then you need to do to describe the statistical analysis. Often they do it in a separated paragraph, and here you check how robust the results are. Here probably it's also either here in statistical analysis or in the patient chapter you get all the details that Professor Bernasconi talked about prospective study, retrospective study, and everything else. Now, physicians, because they also had a reproducibility crisis in the life sciences, want really all the details. Some of us, for us, are kind of ridiculous, but if you said, I implemented this in Python, that won't work, because when they say I added the saline solution, which is the most standard chemical compound you can find in an hospital, often they want to tell you, I bought it from such manufacturer in this plant and with these lot numbers. And so even when you say Python, they generally want you to write which version, libraries, which version, and so on, and so on, and so on. And some of this is really redundant. It comes from they wanting you to know which exact reagent you use, and so on. However, there has been also a reproducibility crisis in AI results for the reasons we have seen this morning. And nowadays, for good reproducibility, they really, really like you for very good studies. If at least you put a GitHub online, but the recommended way would actually be like a Docker that is not your code, it's not really some code, but it's something that you are able to run. I said I didn't prepare slides about that, but there have been studies about reproducibility of AI results, and they found that of 30% of the paper published, they weren't able to run the code, to reproduce the code that the author was claiming to have written. And there was another 10% where the code was available, and not even with the help of the original authors, they were able to run it and reproduce the results. So that's why, in this background, if someone tells you that they have a 95% accuracy while the previous results was 93, trusting that becomes very hard if you cannot even run the code. Next section is results. Here you are supposed to describe what was found. And here you describe very quickly and very objectively what you found, plots, table, statistical tests, and whatever. And objectively means that you are not supposed to say much, few, or things like that, but should say odds ratio are 1.3 pair, and so on, and so on. And finally, discussion. This is more qualitative. You put your finding in the context of the other research that there is, and you describe the results and how they can be useful. Generally, here there's a bit of leeway about self-judging yourself. In good work, you should show some awareness of the potential limitation and potential confounders you haven't addressed in your work, and you might describe what's next. So when you prepare a presentation about a project, you should find some, you should identify these points, like the materials and methods, so which patient they used, which acquisition they made, which imaging modality, and then to judge it, so to say, you should use this presentation as a guideline to see if the selection criteria are well reported, how they did it, which kind of validation they did, and whether in the discussion they addressed the potential confounders and so on. Okay. And I put here two links to two repositories. One is from the Scientific Reports journal, and there's a topical collection about artificial intelligence and medical imaging. You get, paper have been submitted until September, and so some articles have been just published, and it's about a very varied ensemble of possible application. Like they get image processing. They get image processing. They get classification task. They should also have some here radiomics model. This is probably for all kind of image classification. There are some papers about segmentation. So you can choose whatever paper you like. It's some optimize the architecture, some report about the findings in some specific application. And of course, the most typical paper that researchers do is testing their own model, which is the most common feature more than the clinical effectiveness. As I told you, you are welcome to find some other papers for whatever reason you are working with other topics. Now, the second repository is slightly older because it goes down to 2023. This is about a conference mostly dedicated to engineers, even is for medical imaging, but it's for engineers, so it was much more popular a couple of years ago. So you see that the last occasion they had 15 papers, and it's about addressing lesions in the brain, which might come from glioma that we've seen in some data sets, or multiple sclerosis, but also multiple sclerosis, stroke, and traumatic brain injuries, all of which leave lesions in brain images. And these papers are mostly written by IT engineers, so they are more on the technical sides of how they did it than on clinical application. But for us, it's still very relevant. You can see that we've tried the most different methods, like, I don't know if you ever heard of the segment anything model made by Meta. It's a very interesting neural network, a foundation model behind that, which is able to segment all images from all kinds of objects. It's not trained on recognizing cars or flowers or whatever. It's pre-trained, and then the user can either point with the mouse on an object, or make a bounding box, or write a text description, and it will find the most likely segmentation. It's based on a foundation model, and here they tried to fine-tune it for medical images, because this foundation model has seen exclusively natural images. Okay, so question about this? Yes. You need to select one paper from either repositories or from yet another one, and maybe just send it to me just to make sure it's relevant to the course, but 99% of the case I will tell you it is if you choose anything reasonable. And you can prepare a presentation with either slide presentation, or I don't enforce it, because I don't like PowerPoint that much, but it's not like I found an alternative, so you can use whatever you prefer. And yes, that's it for this part. Other question about the presentation or anything, and keep it to 12 minutes or so on, so that we have some other minutes for for discussion, asking questions. Okay, so if you don't have other questions, I will present then some project ideas. Now that's the requirements that we have come up with in the previous years, and we kept them. So the ideal group size is like 3 or 4. You can, in case, go up to 5. And of course, we will not evaluate, I will not evaluate the performances, but the implementation. And the points will be about image pre-processing. You need to have understood the context of which kind of image you're using, how you evaluated your strategy, and whether you use some tricks to improve stabilities, if you use some especially clever implementation, and you can use whatever tool you want. And you can use some kind of, some of the things that we've done in class as a starting point or as ideas. Now, I will introduce which data I can provide you. Again, like before, if you, for a reason you are working on something else and you want to use, I don't know, to apply to a challenge that's available on the internet, if you want to use some data that you're working on, feel free to do that. But probably will take you more time. It will be more complex. And so what I can give you, it's, as an example, is images from the ADNI database. I've written here that I have 100 MRs and 308 healthy controls and 16 MCI subjects, but actually I also have a full database of like 12,000 images, but that will give, it will take quite more time to process. I've already done some pre-processing to the MNI space, which takes lots of computational resources. And you can really do lots of tasks. You can predict who is an Alzheimer and who's an healthy controls using DMR. You can try to predict on healthy controls the gender from MR or the probability of mild cognitive impairment conversion from PET, or even the conversion from the probability of conversion from MR images, but that's difficult. Or you can also do some unsupervised learning on healthy controls and try to predict, I don't know, some demographics, see what appears within them. And indeed, I can provide images in native space. If you want to work on that, I can provide you some segmentation in classes like gray matter, white matter, and cerebrospinal fluid for the MR images, or the standardized templates. Concerning the BRATS database, you can work with what I've given you, which is 170 patients with 4 MR sequences, and you can do, well, a neural network, I would say, even if it's not mandatory, do a segmentation using convolutional neural networks. And it's generally it works relatively well. You need to understand how to deal with 3D images, which don't really fit as a wall in Colab unless you really think well about the architecture, but you can work on 2D slices and then assemble them later, or but in this case you need to make sure think about the balancing of the classes, because most of the volume is not a tumor. And so it works relatively well, and it's relatively easy to implement. Then I have the pneumothorax DB, which we've also talked about. There are 11,000 cases, which, by the way, it's, I I guess that the prevalence, if I didn't recheck that, but I think that the prevalence of subject with pneumothorax is like 10%, something like that. And of course, the volume occupied by the lesion is a minority, and it's not super easy to spot at the beginning. So you can do one of these two things. So either do a prediction, which can be either the pathology status, or you can predict, try to predict the demographics, or you can do semantic segmentation. You try to find where is the pathology, but however, probably if you do that, you are also able to predict the pathology status. And finally, you have a database of nuclear medicine images for Parkinson database. That's the dopamine transported images, which is, let me say, just to make it short, worse than PET. We are talking about 8mm resolution images. So very poor quality and very poor spatial resolution and very high noise at the same time, but they still are very informative for Parkinson's disease. And also here you can do some, the data set is unbalanced. It's, again, these times it's 9% the healthy controls, because they don't have really reason to acquire this nuclear medicine modality for lots of subjects. And I can suggest you to do some unsupervised classification of healthy controls versus Parkinson's disease. And you can also try to see, given that the dopamine receptors in the brain in the healthy controls follow a linear degeneration over time, you can see some demographic properties in healthy subjects. And that's it. These are 5 data sets that I can provide you with some mostly feasible tasks. And you can just let me know. Some of the database you already have them, and some I can just share them. Any other question that needs to be recorded on video for others? Okay.